Assalamualaikum warahmatullahi wabarakatuh, and good evening and good morning to the audience wherever you are in this world. So welcome to the 95th Distinguished Lecture Series organized by the Faculty of Engineering, University Technology Malaysia. I am Nurul Akmal, and it is my greatest pleasure to moderate this session because the speaker is my former PhD supervisor back in 2007 to 2010. We are very fortunate to have Professor Huajiang Ouyang from the University of Liverpool, UK. Thank you, Prof, for accepting our invitation despite your very tight schedule. I'm sure many of your former students will be joining also here today. So maybe I can share a little bit about my experience doing my PhD with Ouyang in 2007 up to 2010. Okay. I had a very good experience with him conducting my research. Ouyang was a very keen researcher in his field, and he was also a very attentive supervisor. Under his supervision at that time, he had so many students from various nationalities, not only the UK people, and he had also many students from Malaysia, from China, and other nationalities as well. So I think most of us have successfully completed the study with flying colors. And Ouyang, as a supervisor, has brought us to many conferences. He encouraged us to publish many papers, and that actually gave us many opportunities to network and also to learn how to do research properly. So I think for today's session, Ouyang will be talking about his personal overview on his research area, covering structural dynamics, control, and structural identification, just to name a few. If time permits, we will take about 1 or 2 questions for Professor Ouyang to answer at the end of the session. So audience, please drop your questions in the comment box, maybe here or at the bottom. Okay. Before we start with the lecture, I will pass the session to Professor Datuk Rafiq, our Dean of Engineering Faculty, to introduce Professor Ouyang, our distinguished speaker. Over to you, Datuk.
Thank you, Dr. Nurul Akmal. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 95th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I'm the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Huajiang Ouyang from University of Liverpool, United Kingdom. A bit about our distinguished speaker today. Huajiang Ouyang received BEng and MSc in Engineering Mechanics in 1982 and 1985 respectively, and PhD in Structural Engineering in 1989 at Dalian University of Technology, China. He is a full professor at the School of Engineering at the University of Liverpool and the head of the Dynamics and Control Group. Dr. Ouyang is a fellow of the Institute of Physics and a fellow of the Higher Education Academy. He was a Royal Academy of Engineering and Leverhulme Trust Senior Research Fellow in 2009 to 2010. He is also a visiting Changjiang Chair Professor in China. He is a Deputy Editor-in-Chief of Journal of Sound and Vibration, European Editor of International Journal of Vehicle Noise and Vibration, and on the editorial boards of Applied Sciences and Chinese Journal of Computational Mechanics. He has published 265 journal papers and 111 conference papers. His main research areas are structural dynamics and control and structural identification. He is particularly interested in friction-induced vibration, moving load dynamics, structural identification, inverse structural modifications, and vibration-based energy harvesting. So that is a brief biography of our distinguished speaker. Here now is Professor Huajiang Ouyang from University of Liverpool, United Kingdom, with a lecture entitled A Personal Overview of the Research Topics in Ouyang's Research Group. Professor Huajiang Ouyang, over to you.
Thank you, Professor Abdul Kader, for your kind invitation and introduction. And thanks also to Dr. Abu Hussein for the kind introduction and sharing your personal experience with me. Ladies and gentlemen and friends over the world, I feel greatly honored to be invited to give this lecture to all of you. And I hope in the next hour or so, I'll be able to explain what I have done in my fairly long research career that started in 1984. And I hope you benefit from my experience. And after our talk, I'll be very happy to answer your questions. And if you have any ideas of research collaboration, and I would very much like to hear. The title of my talk is Personal Overview of the Research Topics in my research group. I need to stress personal overview. And in my fairly long career, I have been involved in a number of research topics and accumulated lots of experience. And this is only a partial account of what I have done, and it's from a personal angle. Without much ado, I'll come on to the actual contents of the lecture. I'll touch upon 5 main research topics I have given much attention. There are other less touched upon topics I won't have time to cover. And the 5 main topics are as follows. The first one is friction-induced and involved vibration. And it covers several topics, including car disc brake noise and train brake noise. The second main topic is moving load dynamics. I'll explain what it is a little bit later, and followed by structural identification. I also done much work in recent years on vibration and noise control. And a very recent research interest of mine is energy harvesting. I'll talk about these one after another. And given the limited amount of time, I'll only tell you what I have done. And hopefully they are interesting stories. I probably won't have time to tell you how. And if you wish to know more, and please contact me after the lecture. So the first topic, a main topic of mine, is friction-induced and involved vibration. It has been a major research theme for many years. The friction-induced vibration, the idea can be introduced through this very simple model we call a slider on a belt. So over here, you can see there are mass spring systems, and with a slider in contact with a belt which is moving at constant or non-constant speed. And due to the friction occurring at this contact interface, and the vibration excited in this oscillator. And because friction display an interesting phenomenon, the coefficient friction in static situation is usually greater than the coefficient of kinetic friction. So very peculiar kind of vibration called stick-slip oscillation ensue. And vibration can become unstable as well. And then the contact between the slider and the belt may get lost. And the other thing, interesting phenomenon is called stick and slip vibration. Stick means the slider and also this mass travels together at the same speed with the belt. So they are like sticking together. When this happens, the spring gets stretched, and the force within spring become greater and greater until it overcomes the static friction force at the contact interface, and then the slider starts to slide with a non-zero relative velocity. So this cycle of stick-slip and is repeated, and it's called stick-slip vibration. And this kind of vibration has a very interesting dynamic behavior. It's from mathematical point of view, it's called non-smooth because there are two distinct regimes motion, stick and slip. And when the vibration become in the vertical direction become greater, and the slider loses contact. So we are entering another two distinct regime motion. Contact with the belt and the separation as two separate systems in another motion regime. Here I'm showing you a practical machine. The previous slides only explain what may happen in a idealized friction-induced vibration system. Now, this you may recognize is a car disc brake. And when a car is traveling, the disc attached to the wheel travel at the same speed as the car wheel. And then if you apply the brake, there's a friction material called pad on this side and the other side, shown here. And when you apply the brake, the two frictional materials are squeezed on either side of the disc and dissipating the kinetic energy of the disc. So the car is slowed down. Well, friction is well known to be able to dissipate energy, so it's stabilizing, but it can also excite, induce friction-induced noise, which can be very annoying, and it's a headache in car industry and causes a high warranty cost. And it has been a popular research topic for many years. And we've studied this also for a number of years. And one piece of research work we did, actually this was done by one of the UTM colleagues, my former PhD student, Dr. Rahim Abubakar. And this is the pad material. On top of the pad material, we stick a piece of paper which draw the final element model on the surface of the pad. And we run a linear gauge which measures the height of the pad. As you understand, friction material such as pad is rough. However, other researchers always model the pad as perfect flat, but in reality, it's rough. As you can see, if you measure the surface of the pad, and you get a profile like this, and several pairs of pads are measured. So we use the measured data in the FE model, and when we simulate the contact, and these asperities or the peak values first get into contact with the disk, and the contact area would be very different from a perfect flat disk, as you can see. And this is what we measured using the pressure film. The brighter color indicates the higher pressure, while the white area, which is look like missing, that's where the contact is not present under this pressure because of the roughness of the pad surface. So if we use the true coordinate of the pad, and we got the in the simulation use abacus, this is the contact pressure. As you can see, that the bright area shows high pressure, and it's quite irregular, even though superficially the pad looks like a symmetrical structure, but because the randomly distributed roughness, the actual contact pressure looks quite random, and this should be considered if we wish to have better predictive results of the contact pressure leading to wear and also friction-induced vibration noise. The brick model in an industrial standard can have many degree freedom, and this particular model looks very authentic to the real machine, has 5 million degree freedom. And when we carry out the analysis of a brick square analysis, each run can take more than a day using a cluster of the modern best PCs. So it's very time consuming. And if you want to do optimization and design, that's the computation cost can be prohibitive. And one idea to deal with, to cope with the huge computational workload is to use something called a surrogate model. And the surrogate model is a mathematical representation of the phenomenological behavior of a detailed model. I don't have time to get into detail the surrogate model. If you are interested, you can Google and to find out what a surrogate model is. And using a surrogate model established, and we can greatly reduce the computational cost, and then a useful analysis such as reliability analysis, optimization, or design can be carried out within a realistic time frame. Apart from the car disc brake noise, we are also interested in train brake noise, and I've had many research collaboration with one Chinese university, Southwest Jiao Tong University, which is very well known in China in their work on high-speed train. And this slide shows you several different samples of small discs with grooves cut onto the surface. And another one showing groove distributed over the disc surface in another pattern like this. By cutting grooves, we modify the contact area between the disc and the friction material. And that has a serious consequence on the wear behavior and also the noise generated. We can also modify the surface of the friction material. Over here, this is the Fe grade of the friction material, and the left one is the original material without any surface modification. While this one, as you can see, we cut a groove in the vertical direction in the middle of the pad surface. And another one, the grooves appears in the diagonal direction, and this is horizontal. This is diagonal groove in the other direction. And we could also use some rubber soft material behind the friction material to provide a cushioning effect, and hopefully to remove the vibration and severe vibration and noise. And this figure shows the groove cast into the damping material behind the friction material. By the way, in each slide, I also show the paper we published on the topic of the same slide. And this slide shows a number of several different arrangements of the train disc brake friction material. And they look very different from the pad material you will find in a car disc brake. A train has a much higher amount of kinetic energy, as you understand. So the friction material takes in a very different form. They are formed in small blocks and spread over space in a number of configurations, and the size of each block can look very different. The holes are there to dissipate very high heat and produced when the brake is applied. And train noise can be a big nuisance and is a hindrance to the construction and development high-speed railway in China and elsewhere. When train run near the residential area, there would be a strong opposition to the construction, and redesign or reroute a railway line can be hugely expensive. So one thing the authority wishes to do is to understand how vibration and noise are generated and transmitted. And one calming measure of noise is to come up with a different material and different brake design to curb, to suppress friction-induced noise, where can also be an issue when the load, the brake load is big, as in the case of trains. This is another topic related to friction in railway industry. As you can see, a wheel set is traveling on a two-piece rail, and there's a high friction present at the contact interface for traction. And over time, the rail surface and certain wavy shape appears on the rail surface called corrugation. The wheels themselves can lose material due to wear and vibration and become, lose its roundness. It's called a polygon. It takes on a polygonal shape. And the corrugation on the real surface and the polygon shape of the wheel, as you understand, will increase the chance of vibration and its magnitude, and further degrade the wear and cause premature failure. And these are also related to friction. Another problem related to friction is shown here in schematic is the aero engine. These are meant to represent the blades, and in between the blades, and there's something called friction damper. And while the blades rotating and vibrating, and there's a relative movement between the blade platform and the friction relative movement. So friction is generated, which dissipate vibration energy. So that's about the first main topic, friction-induced and involved vibration. The next one I've been working on is called moving load dynamics. And loads usually are stationary relative to a structure they are acting on. But for a number of problems, the load acting on a structure actually travels in relation to the structure. For example, a train running over a bridge. When a train gets onto a bridge, initially it's only part of the train, and then the whole train on the full stretch bridge, and then the train leaves the bridge. And this presents something called a moving load. And this figure shows a simple idea of so-called moving oscillator. You see a simply supported beam here. On the beam, there's a point mass, and the mass is moving at a certain speed. And as you understand, when the mass moves, it adds a time-varying inertia to the beam. And while the beam is traveling and in contact with the beam, and the mass also presents a time-varying stiffness and superficial damping, even if there's only a mass. And if you look if you are interested in this problem, and you can read this easy to understand paper I wrote for mechanical system and signal processing. It's called Moving Load Dynamic Problems, a tutorial with a brief overview. By tutorial, it meant to targeting the general audience, and it's good for self-study. And practically, this shows a laboratory structure of a moving load problem. The photo is fairly crowded, so let me explain to you. This is a long beam or plate structure. It has 4 spans supported here, and it is meant to represent a 4-span bridge. On the bridge, there's a model car, and we run this model car along the bridge, and we measure the vibration excited by the moving car using laser displacement transducer. We have one for each span. And underneath, you may also be able to tell there's a actuator for each span. You can see 3 of them. The 4th one is masked by the support. And this is a representation of a vehicle track and bridge interaction I mentioned. You probably won't be able to tell the track. You can see these lines. These are the metal track glued to the bridge structure. And schematically, and it's shown here, we have these supports of 4-span bridge, and the actuator provides some force over here, and we have a moving car. We tested one a big bearing ball of several kilograms as moving mass. 1 ball and 2 balls separately. We also tested the excitation caused by 1 car and 2 cars, shown here. And the car is modeled as multi-rigid bodies with springs and rigid mass and rigid bodies. And we can model the bridge in very good details by through a finite element model. And there are also other moving load problems I've been involved in, but due to the time limitation, and I'll skip those. The third topic I'm coming to is the structure identification. By identification, we mean it's an inverse problem. If we use a system terminology, in a control system, there's an input applied to a system, and then output is produced in the system. So if we usually, in our conventional analysis, we know the system. For example, we model the system use the finite element method. We apply an input, which is false, and then we predict or examine the response, which is in a dynamic context is the vibration or the frequency of the system. So there's an input, system, and output. The conventional analysis called forward analysis is given the input and the system, we try to predict the output, and that's usually is easier. Now, if you know the input and you measure the output, you try to say what the system is, you characterize the system, and that's called an inverse analysis. And to be precise, to try to characterize the system called system identification is the first kind of identification problem. In the second kind of identification problem, we measure the output. We suppose we know enough about the system. We try to work out what the input that excites the output. That's called false or input identification. And we do both inverse analysis, but we are more focused on the system identification. One of the system identification is called model updating. We all know FE model is very accurate with a caveat on condition the material properties and the geometrical properties used in the FE model are accurately captured. But this is not guaranteed. And usually, material property, for example, mild steels is widely used in building machines and structures. And what we often do is we pick up a value of the mild steel, for example, the Young's modulus. If you look up a material handbook, and you find its nominal value, which can be 205 gigapascal. But the real Young's modulus value can range from 190 gigapascal to 210 gigapascal with a random distribution. So if you use nominal value, the Young's modulus itself can give you error of several percent even before you carry out any structural analysis. And there are other material properties which are not well known. And if you don't measure them, identify them, and you use nominal values or guesstimated values and the FE model, even if using a huge amount of elements, will have a limited predictability. So that's the material side of structural analysis. Geometrically, sometimes we don't know the geometry. For example, when we for welded structure, we study like this one, and this is represent a structure assembled through joints, welded spot welded joints and the booty joints. And the welded joints, the spot welds, after two components are connected through spot welds, the spot weld is hidden underneath, in between two components welded together. And the precise of the spot weld is now known. So even on the geometrical side, sometimes, and the dimension, the input data is not well known. And booty joints works through a pre-applied load and the frictional torque. Again, the friction torque affects the stiffness and the damping of booty joints. Again, that friction load, friction torque is not known usually. And this is another structure and actually studied by two Malaysian PhD students of mine, and who I hope are present as well. And these are the structures they studied while they were in studying for PhD at Liverpool. This is another interesting identification problem. Here you can see a shaft with gears and discs. And the goal of this research is to identify the torsional receptors of the shaft, which is very useful for design and vibration control. But torsional receptors is very difficult to measure. And the difficulties lies in two aspects. The first one is it's difficult to apply a known torque to a rotor. It's easy to apply a force, and in a test you can use hammer and to hit a structure to provide impact force, and the impact force is measured as input. But it's difficult to apply a torque to a structure, so the input is difficult to apply and capture. And the output, which is the angle twist, is more difficult to measure than translation. And due to these two difficulties, and the torsional receptors is poorly measured. And we devise an indirect method in which we added additional structure like this. We call T-shaped structure shown here. And this structure is very simple. We add this structure, and when we use hammer to produce a force at the end here, and the torque is imparted into the structure. And through the linear accelerometers, we are able to interpret the angle twist over there. And this is the assembled structure. Through measuring the receptors of this assembled structure and using our method, we are able to identify the receptors of this substructure, which is the original rotor we wish to measure. And this is the philosophy called receptance coupling. I would like to highlight this method. In order to measure the receptance of the original structure, which is complicated or difficult to measure, we intentionally introduce an additional simple structure. We measure the receptance of the simple structure, and we also obtain the theoretical receptance of this simple addition structure. And then we are able to work out the receptance of this substructure, which is the original structure you wish to measure. And this paper is published in Mechanical System and Signal Processing. And the first author is a PhD student from Taiwan, and this is his supervisor in National Tsinghua University in Taiwan. And this slide shows a picture of friction material. And friction material actually is orthotopic material, but in the FEM analysis by most researchers, and the friction material is treated as isotopic material. In order to find out the material property of this orthotopic material, and we carry out a comprehensive test campaign, and from the measured frequencies, and we are able to identify the 9 independent material parameters of isotopic material. The challenge here is the pad material is quite small. It's very difficult to excite a number of frequencies we need. As I said, there are 9 independent material parameters for orthotopic material model. And you probably know, in order to identify 9 parameters, you need to have reliable measurement more than 9 pieces of information, frequencies in this context. But because the pad is small, it's difficult to excite more than 9 frequencies. And that's one challenge. The other challenge is it's easier to excite frequency of the lateral bending modes, but we have to excite in-plane modes of the pad because some material parameters governing the orthotopic material are sensitive to in-plane frequency, but not out-plane bending frequency. So that's a second challenge. I won't have time to go into the detail of the identification procedure. So I'll move on to another identification problem, which is damage identification. And this photo shows a cantilever beam and connected to a shaker and excited by a shaker. And there are 2 cracks cut into the beam, and they are marked here on the other side. Yeah, so you can't see the crack, but we mark them so you can see where they are. And we use a scanning laser vibrometer to measure the vibration of these points. We scan through. So this green square shows where the velocity are measured by the scanning laser vibrometer. And from the measured results, we are able to localize the crack. So we find their location, also quantify the relative severity of these cracks. We also carry out so-called stochastic identification. As you understand, many real structures have material inhomogeneity, and also due to manufacturing variance, and the material properties and the geometric properties are not certain. So there's a range of uncertainty. And we studied cracks in a plate, also a bolted structure like this. There are 2 hat-shaped structure are bolted together by 10 bolts, and each bolt behaves slight slightly differently. And in conventional mode of dating, we'll identify the the stiffness of the bolts as average. But because each bolt behaves slightly differently, and it would be more useful to find out their stochastic properties, for example, the mean value of the stiffness, and also standard deviation and other stochastic properties for characterizing the uncertainty of these bolts. And a similar structure was also tested and studied by your colleagues at UTM and Dr. Abu Hussein, which was published by in Mechanical System and Signal Processing. This slide shows a picture of a plate with two areas shaved away some thickness. And these can be treated as damage or degradation. And we use laser vibrometer to measure the moles of this plate excited by shaker. And we are again able to identify the location and the relative severity of these damage. And these are the where the work was published. We also look at the identification bolted joints for aero engine cylinder and show in this model. And seam weld of a T-shaped plate. So one plate welded through a seam to a horizontal plate. And we deliberately leave a gap between seam weld, and through experiments, and we aim to identify the location and the size of missing weld. And another one is to identify the multiple damage of this frame structure, and the cracks are shown here and there. There's more than one crack, and they appear at different locations of the structure. In recent years, we also carry out some interesting vibration control work. And our work is distinct from many other researchers. One philosophy of vibration control is so-called structure modification. Quite often, we find a structure due to service, normal tear and wear, and the structure degrades and its material or geometrical property have been changed. And from a dynamic point of view, their mass difference have changed, and leading to changes, unwanted changes of frequencies, modes, or modal damping. And through structural modification, we are able to restore the original health of the structure. Or in a different scenario, suppose a structure is originally designed to perform certain function, say working as a school, but then the function of the structure must be changed, say, to become a factory. And then the frequency and the modes will need to be changed due to its new function. And the question is how to achieve the new frequency and modes through a small modification to the original structure. And we carry out a number of research projects. And this particular one is called frequency assignment. And through modification of this dual shaft gear disc system and using small pieces of mass on the disc, we are able to tune the structure to the desired frequency. You might be thinking this is easy, but what we do is using the inverse analysis. The scenarios is like this. Given a known structure with known frequency, and you want the structure to have new frequency and modes. And how do you modify this structure to get those frequency you want? And that's an inverse analysis rather than a repeated trial and error forward analysis. So through our research, we are able to identify the required structural modification so that the desirable frequency and modes can be achieved. This slide shows a successful story of a real application of frequency assignment. On the left is a machine and with a rotating disc, and underneath there's a stationary structure. And this structure is called a brake clutch. So it functions in one aspect as a brake, in a different aspect as a clutch put together. And these machines, when in operation at high speed, gives out a high frequency noise called squeal. And through theoretical and experimental research, we are able to identify the mass and stiffness needed in order to suppress this high squeal noise, high intensity squeal noise. And what is shown here is stiffness we connect to the disc. When we connect this stiffness, and squeal would disappear. If we remove it, and squeal will come back, as shown in this measured time frequency plot. What is shown horizontally are the frequency of the noise measured. And over here is the time. So as you can see, from time 0 up to 32 seconds, when the springs is removed. So during this period, 0 to 32 seconds, when the spring is present and the intensity of the friction noise is very low. When the spring is removed at 32, as you can see, these bright colors bars appear, representing the emergence of high intensity sound at those frequency 8K and slightly over 12K and so on in very bright yellow color. So indeed, this demonstrates the identified stiffness works to suppress the squeal noise. Without it, and squeals will appear. The other work we did in collaboration with my Chinese colleagues is so-called Quasizero stiffness isolation. And you probably know, and for isolation vibration, the stiffness should be very low. You understand the cushion of a car, a seat need to be very low, very soft. But a very low stiffness would be detrimental to static loading. So ideally, the stiffness should be very low for in a dynamic contact and high in a static context. And the ideal quasi-zero stiffness isolation emerged several years ago. Quasizero means the spring within certain range of deformation would present a nearly zero value. So it's very low in dynamic context, but in a static loading, it's reasonably high. And this one design, a Quasizero oscillator, and it's used in this trolley that carries with a chamber that carries a newborn baby. A newborn baby and is prone to vibration damage to their brain. So when a newborn baby is transported from one room another room in a hospital or in an emergency context in an ambulance, and the oscillation from the floor transmitted through the trolley can cause some irreversible damage. And using this Quasizero stiff isolator to build this isolator platform, and the vibration can be greatly reduced. Both theoretical work and experimental work has been done on this structure. Another application is the so-called Steward Platform, widely used in vibration control. And the underneath the platform, we install a number of Quasizero oscillator, and so the platform can have vibration isolation in all 6 degree freedom, 3 translations, 3 rotations. Another interesting vibration control problem is called band gap. As you may know, on a periodic structure, a wave can travel in a certain range of frequency. That frequency range is called a pass band. Wave can pass. But wave cannot travel far in a certain different range of frequency. And that's called a stop band or band gap. This phenomenon has been known for many years, but in recent years, the emergence of the metamaterial has stimulated renewed interest in this idea in vibration control, and provided new opportunities for controlling a wave transmission. And this slide shows a particular structure to prevent a periodic structure in this form. The structure consists of a number of so-called cells with its own detailed structure, and it's arranged in this direction, and it can stop wave transmitting in the longitudinal direction within certain frequency bands. And this is also successfully tested on a real structure. And another noise control idea is so-called Metasurface. And this is the photo of a number of small cells produced. And they are identical. So one wave hit this surface, it can be manipulated by this Metasurface and focusing at a point. It can do a number of other things, but given the limitation of time, and I won't come into the detail of these. And very quickly, realizing the time that has gone by, I'll come to the very recent research interest, which is energy harvesting. We are working on something called tribal electrical energy harvesting that makes use of the friction induced vibration to produce electrical energy. And this is a simple 3 cantilever structure being tested on a shake table. And this is another idea of a slider and under external excitation, it will oscillate within this capsule structure, and due to friction at the wall and impact at the end surface, electricity is generated. We are also working on electromagnetic energy harvesting using this flywheel and horizontal excitation. The flywheel will work as a pendulum and causing rotation as this pinning gear, which will turn a generator to produce electricity. Test has also been done. This is in collaboration with some Chinese colleagues. And before I finish, I need to acknowledge these institutions to sponsor my research. And last but not least, I need to pay tribute to my large number of collaborators in China, in Malaysia, and some other countries. And these are the institutions I've been collaborating with. I have the great fortune of having 7 Malaysian PhD students over the years. And they have produced very high quality work. And I hope to be able to continue my collaboration with them. I think that's all I wish to say today. And sorry for the overrun of the talk. I'm happy to answer any questions. Thank you very much for your attention.
Okay, thank you, Professor Ouyang, for the very informative sharing. Now we move to the question and answer, and I will read out the first question from Dr. Muhammad Kamil Abdul Hamid. For your information, Prof, Dr. Kamil is working closely with Dr. Abdul Rahim Abu Bakar. So the question is, what is the best approach to minimize the friction-induced vibration problem?
That's a good question, but as you can see from my talk, there is a number of friction-induced vibration problems. So to give you a good answer, it needs to be specific, whether it's disparate noise or is it, say, a noise in a bolted joints. So could the question be more specific? It could be from the, yeah, go on.
I think it's relating to brake noise.
Okay. Now, it could be from a material side, but there's a limited choice of material. So usually we'll work on the structure side. And one thing to do is commonly used measure is to modify the friction material by shaving the leading edge and trailing edge. Also cut the groove over the material surface. You could also use damping material, but damping materials are quite expensive. Recent years, they are cheaper alloy, high damping alloy. We are also studying, but we feel the best way is to modify the structure of the friction material, and that's also has been trialed in industry by a number of researchers. And the key is to come up with optimal configuration of the friction material, and research is still going on.
Okay, thank you. We can move to the next question. Okay, I think we can skip this one. This is for the organizer. We can move to the question from Dr. Shahril Sani. Yes. Okay, Dr. Shahril Sani is also your former PhD student, Prof. If you, I'm sure you still remember him. The question is how to identify nonlinear complex model resonance interaction.
Nonlinear resonant. Can you repeat the last bit?
Strongly nonlinear, complex model or resonance interaction.
Strongly nonlinear
Yes.
structure. Okay, that's that I would say very difficult. By strongly nonlinear, usually we mean there's no linear stiffness. Say, for example, a Dufin oscillator, most people will know, has a linear stiffness and also a cubic stiffness. By strongly nonlinear, usually there's no linear stiffness, so it's always behave nonlinear. Or in a different way, the coefficient for cubic stiffness term is very, very high, so it's dominant. It's dominant over the linear one. In this case, one strongly nonlinear structure excited, and the behavior is chaotic. And that presents lots of difficulty because it's chaotic. And each time you do simulation, you do measurement, and the measure time history are very different. And I think you have to use some measures. When I say measure, it's not the experiments. I mean mathematical measures, quantities, and use in chaotic vibrations, such as the Lyapunov exponent and some fractal dimension and other fanciful concepts of fractal dimensions as a representation of the nonlinearity. So large number of simulation must be done to in order to get a hand over what appears may represent what is underneath. I would recommend a simulation of 1 degree freedom, highly nonlinear, strongly nonlinear, single oscillator first to establish the a basic understanding how the system behaves, and then move on to do test on just a single degree freedom oscillator.
Okay, thank you. I think we can. I can add one final question because of the time. I would like to seek your view on the prediction of structural damage using model updating, especially for jointed or hybrid structures.
It has been a big challenge to identify either material property or geometrical properties. It is difficult, and the research now, I think, is nowadays is very difficult to. It has come that the methodology has matured over the years. So from the scientific point of view, it's now very difficult to come up with new idea. And now the trend now is so-called baseline free. So there's no initial intact structure to compare with, and also data driven. So there's no FE model, because if you use a model to do damage identification, and the building model itself can take time, also need model updating. So the current trend is data driven and baseline free and identification, and which is widely used in machine health diagnosis. And the mathematically is time series analysis and signal processing. But it's now difficult to make a big impact in the original contribution to the theory of inverse analysis. I would say that in practice, and there can be a lots need to be done, and the work is focused on denoising, and and also identify incipient. Incipient means early stage damage. So when the crack just appear, and how to detect them in practical situation. So there are a lot of challenges in practical situations, and it involves lots of details. So I don't think we have time to go into that kind of detail.
Okay,
today.
maybe we can communicate further in the email,
Yeah,
Prof.
in private.
Okay. Okay, I think that is all the time we have today. On behalf of the faculty and University Technology Malaysia, I would like to thank you again, Prof. Ouyang, for your precious time, and I hope we can expand our collaboration with you in the future. I'm now passing the session back to our Dean, Datuk Rafiq, for the closing remarks.
Thank you, Dr. Excuse me.
Thank
you, Dr. Nurul Akmal, for moderating the session and for introducing our distinguished speaker today, Professor Huajiang Ouyang. And to our distinguished speaker, thank you so very much, first of all, for accepting our invitation to speak at this UTM Engineering Distinguished Lecture Series and for a great sharing session. And to all our viewers worldwide, thank you for watching this webinar series. Do stay tuned because we have many more interesting lectures for you. So until next time, bye-bye for now. Assalamualaikum.
Salam. Thank you all.
Thanks to everyone. Have a nice day. Bye-bye.
And you too, Prof.
You too, Prof. We can communicate further later.